Okay, so here are the homework solutions for verifying trigonometric identities. So we have these fundamental trigonometric identities. They're on page 354, the beginning of section 5.1. So we use those as well as some algebra to try to show that both sides of the equation are the same. You typically work on the one that's more complicated and try to reduce it to one that's to the same as what's on the other side. Now, if they both look similar, then you just have to do some manipulation. So the first one here, you can see the left-hand side looks more complicated. So what we would do is we use FOIL. So you get 1 times 1, which is 1. Outer would be negative sine theta. In would be positive sine theta. So sine theta minus sine theta is 0. So the inner and outer cancel out. And then you end up with 1 minus sine squared theta. So that's left-hand side. And then we take the Pythagorean identity, which is in that table, and if we subtract sine squared from both sides of the Pythagorean identity, we get that, so we can then substitute in, and so we get cosine theta on the left, which now is exactly what's on the right. And so at that point you have verified the identity. Remember, identities are good for any values of theta. Okay, the next one, they both look pretty similar, so we'll just work on the one on the right hand side. And because they involve squares, the Pythagorean identities look like a good choice to try. Now I have to do a little thinking about, notice this has sine only. So since the right hand side only has sine, it makes sense to solve this Pythagorean identity for cosine. So you'd have 1 minus sine squared of beta. If you plug that in, you'll have 1 minus sine squared beta for cosine squared minus sine squared of beta. And then we can combine the two terms that involve sine. So it's 1 minus 2 sine squared beta. And that now equals the right-hand side. And therefore, we have verified the trigonometric identity. Okay, number 3. So the left-hand side is sine to the sine of theta squared. We got sine of theta to the 4th. And we want to show that's equal to cosine squared minus cosine to the 4th. So what I would do is you could factor out sine squared theta maybe. And what you'd have left is 1 minus sine squared theta. So if you take sine squared times 1 and sine squared times sine squared, you get that. Again, back to this Pythagorean identity. So if I solve for the sine of theta, it's equal to 1 minus cosine squared theta. Also, if I solve for the cosine of theta, it's equal to 1 minus sine squared theta. So here, for sine squared theta, I can put in 1 minus cosine squared theta. And for 1 minus sine squared theta, I can put in cosine squared theta. And if I multiply that out, I'll get cosine squared theta minus cosine to the 4th theta, which is what I have on the right-hand side of the original expression. So that is my trigonometric identity. Solved or proven, verified. And the last one, we've got the cotangent cubed of x over the cosecant of x. So none of these are squared. So what I would think of doing is, actually this one's pretty straightforward, I think. So if we what we could do is, you can see we've got cotangent here. So if I take cotangent of x, that'll leave cotangent squared of x divided by cosecant of x. But the cotangent, now it's squared, so it's probably one of those Pythagorean identities. So I've got 1 plus cotangent squared of x equals cosecant squared of x. So if I subtract 1 from this Pythagorean identity, I'll get cosecant squared of x minus 1. So if I plug that up here, I'll have cotangent of x times cosecant squared of x minus 1 divided by the cosecant of x. Something doesn't look right. Let me just check the problem statement and make sure I wrote the problem down correctly. So this is cotangent. Pause for a second. Okay, so I wrote the problem down wrong. So this is cosine. So this should be cosine, not. Well, this is true, but what I'm looking for is cosine. So I can see what the path now is. So the cotangent is the cosine divided by the sine, and then I divide the whole thing by the cosecant, which is 1 over the sine, and then I multiply by cosecant of x, cosecant squared of x minus 1. So these signs cancel out, and I'm just left with cosine of x times cosecant squared of x minus 1, which is the same as I had there. So verify the identity that way. Okay, next group. So looking at the next one, which is 5, again we're trying to show that we can convert the left-hand side into the right-hand side. So when you have kind of a product of functions like this, what you can do is you can rewrite them in their sine and cosine form. So the secant is 1 over the cosine, the tangent is the sine over the cosine, and so we get 1 divided by the sine divided by the cosine squared of x. But dividing by something is like multiplying by the reciprocal. So we get 1 times the cosine squared of x over the sine of x. But the cosine is equal to the, we can do that using the Pythagorean identity, sine squared of x minus or plus cosine squared of x equals 1. So if I solve for the cosine, I'll have 1 minus sine squared of x, so I can plug that into here. So I have 1 minus the sine squared of x divided by the sine of x. But you get 1 over the sine for the first one, so we can break this up into two fractions. 1 over the sine minus the sine squared over the sine. 1 over the sine is the cosecant of x, and the sine squared divided by the sine is the sine of x. And there you go. Now that I've manipulated the left-hand side to be the right-hand side, and we verified the identity. Okay, next one, I think what we can do is we can use the reciprocal identity to rewrite the secant as 1 over the cosine, like that. Then we can find a common denominator, so you'll get 1 over the cosine of x minus cosine squared x over the cosine of x. So just multiply the numerator and the denominator by the cosine, so you get 1 minus the sine squared of x divided by the cosine of x. But the Pythagorean identity says that, no, what am I doing here? I got a little ahead of myself. This is cosine. 1 minus the cosine squared. But 1 minus cosine squared is equal to sine squared of x. So I get the sine squared over the cosine of x. And so there's my sine. And so we could break that apart into the sine of x times the sine of x divided by the cosine of x. And the sine of x over the cosine of x is the tangent of x. So that's all done on the left-hand side, and now I've shown that it's equal to the right-hand side. Okay, and the next one, it's got two fractions, so I think what we could do is we could find a common denominator, maybe. One way to do this would be you could write the cosecant as 1 over the cosecant as the sine, and then multiply by the sine over the sine here. So now I've got, it's just it's a single term in the denominator. Here, if I multiply these two together, it would just be a little more complicated. So what we're left with in the numerator is we have this common denominator, the sine of x. In the numerator, we have 1 minus sine of x squared, or sine squared of x, over the sine of x. But 1 minus the sine is the cosine. Oh, yeah. But then we'd end up with like the previous problem. So what you can see is that this is, well, that was a lot easier. Actually, I'm making it more complicated than it is. All you have to do is use the reciprocal identities. 1 over the sine is the cosecant, so we replace 1 over sine with the cosecant, and 1 over the cosecant is the sine. So there you go. That's all there is. That's a lot easier than I thought. Okay. Number 8, we've got the cosine times the cotangent divided by 1 minus the sine of theta. So typically, oh, and minus 1. So typically, you want to make this into a Pythagorean type identity. So you're going to multiply it by 1 plus sine theta. So we will take the first term and multiply by 1 plus the sine of theta in both the numerator and the denominator. So in the numerator we have cosine of theta, cotangent of theta, times 1 plus sine theta, all divided by 1 minus sine squared of theta. But 1 minus sine squared is the cosine squared. So we get the cosine of theta, cotangent of theta, times 1 plus sine of theta, all divided by the cosine squared of theta minus 1. Let's rewrite the cotangent as the cosine divided by the sine. So we have cosine times cotangent, and then we have cosine times cotangent, which I just rewrote. Again, I'm going to rewrite that as cosine times cotangent, which is cosine over sine. This is the quotient identity, and then times the sine, all divided by the cosine squared of theta, and that whole thing minus 1. Notice sine cancels out. Here we have cosine squared. Here we have cosine squared. So we have cosine squared here. So if you cancel out the cosine squared here with the cosine squared there, you get sine 1 over sine theta. And here we get cosine squared divided by cosine squared is 1. So you get, this becomes cosine squared sine becomes 1, negative 1. These cancel out. All you're left with is 1 over the sine of theta, which is equal to the cosecant of theta, which is what we were looking for the right hand side. Okay, so it's that was a tricky one. Let's review that one. So we took the original expression, multiplied in the numerator and the denominator by 1 plus the sine theta. So the denominator became 1 minus sine squared theta. Replaced 1 minus sine theta, sine squared theta, with cosine squared theta. We also rewrote the cotangent as cosine over sine. And by the time you simplified things, cosine canceled out with the cosine squared, you're just left with 1 over sine. Here you have cosine squared canceling out with cosine squared, which gives you 1, which cancels out that. Okay. I was a little worried there for a minute. Now, the next one, there are these things called, if we go back to section 1, and you don't have to memorize these things. So you look, what we're looking for is, what is the identity for the tangent of pi over 2 minus theta? Those are called cofunction identities. And so it says tangent of pi over 2 minus x, or u, is equal to the cotangent. So this is cotangent of theta. So I can put that in, cotangent of theta, and I multiply that by the tangent of theta, which is the second term. The cotangent is 1 over the tangent times the tangent. Those cancel out. You're left with 1, which is equal to the right hand side. So that worked. Okay. So I think what we're on 9. Okay, number 10. Okay, let's think what we can do here. Might be able to just rewrite all this stuff in terms of sines and cosines. Those are called quotient. So you got the sine over the cosine, and the cotangent is the cosine over the sine. and the tangent of x is the sine over the cosine, and the cotangent is the cosine over the sine. So when we divide, so we're going to make two fractions because we have two terms. So you got the sine of x over the cosine of x divided by the sine of x divided by the cosine of x. So what you would do is you would take the reciprocal of this, the whole thing, and multiply that, and those we cancel these out. So what you're left with is the sine of y divided by the cosine of y, because you take the reciprocal of that. And the same thing applies here. When you divide this by the whole thing here, these cancel out, and you're left with that, but they get flipped around like that. Now the sine of y over the cosine of y is the tangent of y, and the cosine of x over the sine of x is the cotangent of x, which equals the right-hand side. Check. Now I'm going to just to remind you what we're doing here. So we're taking the first term in the numerator. We're going to divide by this whole thing. So what you do is you take the reciprocal of this. So you'd have the cosine of x over the sine of x. So that's the reciprocal of this part. Hello. Okay, so the last one from this group, we have secant squared of pi over x. So that looks like one of those cofunction identities. So if you look again on page 354, you'll see that there's this identity, the secant of pi over 2 minus u equals the cosecant of u. So what we can do is we can replace the secant with secant of pi. So this is the secant of pi over 2 minus x quantity squared. So that becomes the cosecant of u squared. So that's the first term, becomes that. Minus 1 equals the cotangent squared of x. And the cosecant of u, well, we can put x in there, cosecant of x. So cosecant, this becomes cosecant squared of x minus 1. And then there's the Pythagorean identity involving the cotangent and the cosecant. So the cosecant, 1 plus cotangent squared is cosecant. So if we subtract 1 from both sides, you get the cotangent is equal to cosecant squared minus 1. So cosecant squared minus 1 is the cotangent squared, which equals the original right-hand side. So we verified that identity. Okay, the next one says use the graphing utility to determine whether the equation is an identity. So we're talking about that in the lecture. Basically, you plot both of those functions and you see that it's true, and then if it's true, then they line up. So whatever graphing utility you want to use. So I've got 2 plus the quantity. That's the key thing here, is that when you have cosine squared, you have to take the cosine of the thing squared. Minus 3 cosine of x to the 4th power. Okay, so that's the right-hand side. And then we'll plot the left-hand side, which is the sine of the quantity, the sine of x squared times 3 plus 2 times the quantity cosine of x, quantity squared, close parenthesis. And let's just make sure I did that right. I think I did. Graph it, see if they're the same. Ooh, something's wrong. Either they're not an identity. Most likely I just did this wrong. 2 plus cosine squared minus 3 times cosine to the fourth. The second one is sine squared plus times 3 plus 2 cosine squared. It looks right. So maybe it isn't. Let me just pause. Okay, so it's not. That's why it doesn't match up. So because it's not, we don't have to verify it. So the next one is secant to the fourth. So we take the secant of x, raise it to the fourth, subtract tangent of x, raise that to the fourth, and then we'll plot the right hand side, which is 1 plus 2 times the tangent squared of theta. 1 plus 2 times tangent of theta squared. Graph that. Okay, so you can see there that they are the same. Now you're like, what's that red line? Well, yeah, that's where the asymptote is, but otherwise they are exactly the same. So we can just kind of ignore that little. So now that we've shown that that actually is true, let's prove it. So we have secant to the fourth minus tangent to the fourth of theta. So what I would think about doing there is I would say it's secant squared theta minus tangent squared theta times secant squared theta plus tangent squared theta. Why I'm doing that is because I'm trying to come up with some trigonometric identity that involves squareds, and so there is this trig identity that involves secants and tangents, and let's write that out and go back to the beginning of chapter 5. So we've got 1 plus tangent squared theta equals secant squared theta. So if we subtract tangent from both sides, you'll get secant squared minus tangent squared, which is what we have here. So we get, this is the Pythagorean identity. So this becomes 1. So what we're left with is secant squared theta plus tangent squared theta. Now we can use this thing again because we're trying to get something involved tangent squared. So if we use this again and replace secant squared with 1 plus tangent squared theta. So I'm replacing secant squared with 1 plus tangent squared. And then I have my second term here, tangent squared. You get 1 plus 2 tangent squared theta, which is what I have on the right hand side, and that's why when I plotted it, they looked the same. Okay, next one. Let me just squeeze this up a little bit so I can see the whole thing. Okay, so here we go. So the right hand side, this is, you got to be a little careful with parentheses here. So what we have is the sine of x cubed. Notice I put the first parenthesis was to make the numerator in parentheses. And I need to put a plus sign here. Plus, so it's 3 sine cubed plus cosine cubed, close the parentheses, that's the numerator. In the denominator I have the sine of x plus the cosine of x, close the parenthesis to get the denominator. And then on the right hand side I have 1 minus sine of x times cosine of x. If I graph that, you can see that I just get one curve. So it looks like that is true. So what are we going to do here? So I was trying to figure out what to do about this because initially I wasn't sure, but it's funny, you know, you do it one time and it just doesn't come to you. And it came back a day later and I said, oh, I bet that's what's going on. So, if you have, this is back to algebra 2, I think, if you have a cubed plus b cubed, that can be factored to a plus b times a squared minus ab plus b squared. So in our case, a is going to be the sine of theta, and b is going to equal the cosine of theta. So this expression, sine cubed of theta plus cosine cubed of theta, can be rewritten as the sine of theta plus the cosine of theta times sine squared of theta minus sine of theta cosine of theta plus cosine squared theta. So this is algebra. All we're doing is substituting sine for a and cosine for b. And so you'll see what will happen is when I plug that in there, this term is going to cancel out. This factor term is going to cancel out with the denominator. So this expression becomes sine squared theta minus sine theta cosine theta plus cosine squared theta. Okay, and then we have the right-hand side still here. So now what are we going to do? Well, let's think about what's going on here. It looks like here we have 1, and so we can take sine squared theta and cosine squared theta and put them next to each other. And the Pythagorean identity says that sine squared theta plus cosine squared theta equals 1. So we have 1 minus sine theta times cosine theta equals the right-hand side, and it actually does equal the right-hand side. So if I plug in the right-hand side, I'll get that they are the same. So I've taken the left-hand side, first factored it like this, canceled this out with that, left with the second parentheses term, group the sine and cosine together, rewrite that as 1. And that's why it actually worked out. As far as plotting it, they ended up being the same function.